previous sessions to find out how to actually achieve that. I'm not going to go through it all again. Right, so share the screen and right. Okay, let's get rid of all this stuff. Let's just do a new one. Okay, so you're creating a temperature control system. So fan unit.
This is what's required on the front
fan
screen.
Unit, temperature controller. Okay, so what you'll need, obviously, if you're trying to control the temperature, you're going to need a numeric control for the temperature. So set temperature, and it's going to be in some range, which you will determine the range by looking at the fan unit simulator. Okay, so if we load, well, let's load that. See if we can. So this is the fan unit simulator, and when you actually have this running, you will see the way it behaves. So if I turn it on, if I run it and turn the power on, so the heater activates, we can see that it started off at 30 degrees and it will go up to 100 degrees, I think, which means that your stuff on your the control and instrumentation elements on your fan unit temperature controller, they want to be in the same sort of range. So basically, there's no real reason for it to go down to zero because it can't possibly go down to zero. So it's going to be somewhere in the range 30 to 100, and you're going to be displaying the read temperature. Let's say that's going to be, we could use any of these indicators. So you could use a meter, you could use a gauge, you could use a thermometer. Everybody tends to use a thermometer. Very boring. And again, this is going to be in the range 30 to 100. I would actually leave this in the range 0 to 100 because it is useful to be able to see if the temperature is 0. Because if the temperature is 0, it means that you've not turned on the 5-volt power on the fan unit. So we should see that come down to 0. Now, the way you're going to be using this is to basically put it all in a while loop. You'll be reading the temperature from the K8055. So to do that, you need to go down to the bottom of this. Oops, down to the bottom here. Select the VI and select the K8055 modified for the simulator. And then the temperature will come out here. But I'm not going to wire any more of this up because I don't want to be giving everything away. I think I gave most of it away last week anyway. Okay, so let's see what that actually does. It's not going to run at the moment because I've not connected anything to this loop condition. I can just connect a constant to that. And now you can see that this arrow up here is no longer broken, which means that this is a runnable program. I mean, it's not a particularly useful runnable program, but it will do something. So I've got the fan unit running. I now run my control, and you can see that the temperature is reading 0. Now this is because I've not got my temperature sensor on. So this is actually showing the temperature of the this is meant to be like the physical equipment, and obviously the physical equipment, the temperature is actually 30 degrees if everything's turned off, because I'm assuming that room temperature in the lab would be 30 degrees. So you can see that the temperature is actually 30 degrees, but the temperature which is being reported over here is saying 0. And that's because the temperature sensor doesn't work until the 5-volt power is turned on. So if we turn the 5-volt power on, we can see that the temperature sensor is now reading, and it's gone off the scale because I've just connected it straight to the output of the K8055, and this is just an 8-bit number between 0 and 255. So at the moment, it's not actually reading degrees C. It's reading this value here, the ADC value. So if that's to make sense, that would need scaling down. So you need to take the number that's coming out of this and convert it from the 0255 range that it comes up with to some sort of sensible conversion. Now, I'm not sure how you would do the conversion. You'll need to take a couple of values from the actual equipment over here and see how the ADC values relate to the actual real temperature. So you can see that we've got 1 point. It's going to be a linear relationship, so you could draw a little straight line graph, and obviously 1 point on that straight line graph would be 100 degrees corresponds to 255, and you'd find another point by cooling it back down to 30 degrees again. Anyhow, what we've got on here at the moment is in the range 0255. So what you do is you measure the temperature coming out of the unit in degrees. So you need to convert this to degrees. Try to work in the proper temperature and proper fan speed rather than the 8-bit ADC values. Compare the set temperature here, so this knob here, compare this with what is being fed to the thermometer, and that gives you your error. Multiply your error by the proportional constant, and that will be the fan speed. Now I'm not going to do that on here. I'm just going to add a controller for the fan speed. So if I create a control, you see it's automatically coming up with fan speed. You don't do this. You need to calculate the fan speed, and I can now control the fan speed using this controller instead. So if I run this again, let's get the right displays. Getting all the displays on is the hardest bit of this. Right, so if the fan speed is 0 at the moment, because the fan speed DAC value, the value which is being fed into the K8055, that's this value here, that is 0. So if I wind this up like this to full speed, then you can see that the fan speed is now 20,000. And all right, if you see this happen, so it's not cooling down. The reason it's not cooling down is because I've not got the fan power turned on. So we turn this on, and now you see the temperature coming down. So with the fan on full speed, the temperature should come down at the speed that you can hopefully see it coming down now. And it will come down to some minimum value. So the minimum value seems to be 30 degrees, and you can see that we've now got another point for the calibration of the temperature graph, which is that 30 degrees corresponds to an ADC value of 90. So you've got 2 points. So there was 1 point for 100 degrees corresponding to 255. Now we've got another one which is 30 degrees corresponds to 90. So being level 6 engineers, we can all draw a calibration curve for that. We can assume it's a straight line, and then we get the equation of that straight line, and we can use that in order to convert the 0 to 255 ADC value into a sensible temperature in the range 30 to 100. And then we would display that on here in degrees. You want this to be in degrees because your set temperature is in degrees, so you can't subtract this value, which is in the range 0 to 255, from the set temperature, which is in the range 30 to 100. Obviously, our read value needs to be in the same temperature range as the set value. Otherwise, the error is meaningless. Okay, and then you're going to take these two temperatures, so the set temperature and the read temperature, and you're going to display it on a chart. Oh, stop this. Can't edit it while it's running. So, waveform chart, because it's going to be updated inside the loop. It's not a waveform graph. And this would be our temperature displays. I'm just going to feed the set temperature from the control knob and this sort of ADC value into the chart, just so you can see how you get two traces on there. So I'm going to feed this temperature and this one into here. So we get that bundle function that we used earlier, put that there. My read temperature is going in the top, set temperature is going in the bottom, and the pair of them will then go onto the chart. And you can see that it's this horrible auto scaling thing. You can see the set temperature is the red one, and the read temperature is the white one. Now that might not be the case when you do yours, it just depends on what you've done in the block diagram. So I can then wind this up like this. You can see that by default it's auto scaling, which is really annoying and useless. So disable the auto scaling and then set the value to values which are useful to you. So obviously we don't want it with the right at the top like that. That's never useful. So let's change that to 100. So you can change the numbers while you're running it, which is useful. So now I've got the read temperature at 90 degrees, the set temperature. I'll change this to the same range as the other one. Obviously, in yours, this will need to be in degrees, but I want it to be the same as what I've got on here. And then you've got your two temperatures updating like that. So you can see that this is going at a rate of knots down here. So if I change this, you can see all I'm seeing is the line go up and down. I'm not actually seeing any sort of an edge on it, so that's no good. So we need to slow this right down by putting some sort of a timing thing in it. And I'm not sure what value that is. You need to do a bit of experimentation to determine what you think is the best value of the delay. I think if I do this now, we should be able to see the step. Okay, so now we can see useful sort of information from the chart. So, and as I said earlier, add a digital display to this so that you can control it more accurately, and you can make it perform a step. So let's say we're going to have 60 on this, I said, and obviously that's gone off the scale. Let's in order to make it work on A to D, I need to make these numbers bigger. Okay, and I'm going to step it down to 80, So I can put the 80 in. I can wait until I'm ready to change it and then hit that number. And we can see that we've got the step in the red one. And then we'll just cool it down. Now, we can't cool it down at the moment because this is actually the minimum. Sorry, this is the minimum value that I can get from the ADC value, because you can see that the temperature is 30 degrees, which is the minimum that this will go to. You're not going to be operating in this region. You will. The whole point of this is it needs to be a closed loop control system, so you can't operate it outside the range where the system can actually perform closed loop control. So it needs to be significantly above the minimum value and significantly below the maximum value. So 60 and 40 degrees centigrade is a sort of sensible kind of region to be operating in. You may find that that step is too big. Your system may be so good that you're better off putting in a step of maybe 5 degrees or something like that. You just have to see how that looks when you try it. Okay, yeah, someone's asked me, I mentioned that you just need to make sure the proportional control is working rather than integral. What I'm saying there is that, let's say 70 to 80% of the marks would be for producing a working controller of some sort, which means a working closed loop controller, which would be the proportional control system. And then you can add marks by adding the integral part, but obviously the majority of the marks will be for getting the proportional part working, because that will tell me that you know how to use LabVIEW. Getting the integral part working is just adding a little bit of extra stuff to it, and the integral part is actually no more complicated than what I did first thing this morning. That is basically the integrator. All you need to do then is multiply the integral by Ki and add the result to the signal that you're feeding into the fan. Okay, so that's fairly trivial. So I'm more interested in the getting the proportional side of it working and performing sensible tests and producing reasonable looking results and picking sensible values for KP. Adding Ki is just a bit of showing off.
We've done the integral part on the 4th of December, which is week 3.
Is that clear?
This third session.
Okay, so is anyone still not clear? I'm not seeing any more messages.